This is Geometry, section 12.1, circles and tangent lines. So to start off, we've got a bunch of definitions here. I have them already written out. I suggest that at this point you pause the video and copy all these definitions down. And then after you do that, I will go through and give a further explanation of each one. All right, so a circle, we started talking about circles in the last chapter. The formal definition of a circle is just a set of points that are equidistant from a center point. So all these points in the circle out here are equidistant from the center point. We know, jumping down, that the distance from that center point to the outside is called the radius. A chord is a segment with both endpoints on the circle. So a segment going anywhere on the circle to anywhere else on the circle. That's called a chord. A diameter goes through, whoops, that was supposed to go exactly through the center of the circle. We already know that a diameter is basically just two radii put together that make a straight line. It's a chord that goes through the center of the circle. Congruent circles are circles that have congruent radii. So if two circles have the same radius, the same length, then we call those congruent circles. That's the only thing we need to compare. Unlike with triangles, we have to compare sides and angles. Well, with circles, there's no angles. We just compare the radius. So if they have the same radius, they're considered congruent circles. Concentric circles are circles that have the same center, so they just overlap each other kind of like a target. They look like this. A secant line is a line that intersects the circle at 2 points. So it's a line, and it intersects at 2 points. That's called a secant line. So the difference between a secant and a chord is a segment, a secant is a full line, so it extends beyond the circle. And then finally, a tangent line. This should be touching at 1 point. Tangent line is a line that intersects the circle exactly once. So it touches the circle and then it moves on. All right, so use the diagram at the right to name the following. Name the circle. So the way we name a circle is we draw this little circle with a dot in it. I mentioned that last chapter, and then we write the center point. So this circle would be called circle A. A diameter here would be HX. A radius would be HA or AH or AX or XA, whichever one you want to use. A chord, so an example of a chord would be segment PI. An example of a secant would be line SN. Okay, so this is a secant line. You could use any of the 2 points on this line. You could call it line PI, you could call it line PN, you could call it SP, you could call it SI. Any of those 4 points would work, but you have to have this line notation on the top. Same thing for tangent line, you have to have the line notation, and we'll call that one SL. It's touching once at B right there. So you could call it SB, you could call it BL, SL, whatever you want. All right, so find the value of the radius. We know that this is a diameter, we know this is a radius. We know that if we take the diameter and divide it by 2, it's going to equal the length of the radius. So if I take 8x plus 10 and divide that whole thing by 2, I would divide each of these by 2, so that would turn into 4x plus 5 equals 5x minus 2. And I just get all my x's on the same side. So I would subtract the 4x and add the 2. Jumping up here, 5x minus 4x is just x. This cancels out. This cancels out. 5 plus 2 is 7. So x equals 7. It says to find the value of the radius, so if I plug that in, 5 times 7 is 35. 35 minus 2 is 33. This one over here, it does not tell us what the radius is, so we'll call it x. That means we have a right triangle. We've got legs x and 8. We've got x squared plus 8 squared, using the Pythagorean theorem, equals, this side would be called x plus 4. Not 4x, we're not multiplying those together, we're adding those two pieces together. So x plus 4 squared. Okay, this is going to turn into lots of work. We're going to have to FOIL this, we're going to have to factor, we're going to have to do a lot of stuff. So what we can do at this point is we could just make a guess. So if this piece is 4, let's assume that it's drawn to scale. This piece looks like maybe it's a little bit more than 4. Let's try 5. So let's see if 5 squared plus 8 squared equals 5 plus 4 squared. Well, 5 squared is 25. 8 squared is 64. 5 plus 4 is 9. 9 squared is 81. 25 plus 64 does not give us 81. So unfortunately, that's not going to work. So let's try 6. 6 squared plus 8 squared equals 6 plus 4 squared. 6 squared is 64. Sorry, 6 squared is 36. 8 squared is 64. So 36 plus 64 equals 36 plus 64 equals 100. 6 plus 4 is 10. 10 squared is also 100. So that actually does work. So this would be 6. Instead of guessing and checking, you could just multiply this out. You're going to have to FOIL this piece. X plus 4, FOIL that out, combine all your like terms, solve for x, you would get 6 the same way. Same thing over here. So we'll work this one out. So we've got Pythagorean theorem, these two, x squared plus 12 squared equals x plus 8 squared. X squared plus 144 equals, if we FOIL this, x times x is x squared plus 8x plus 8x plus 64. So on both sides, this should be x squared, sorry. On both sides, we've got an x squared. So if I just subtract x squared from both sides, that goes away. Then I have 144 over here. 8x plus 8x is 16x plus 64. I would subtract the 64. We end up with, let's see here, we end up with 80 equals 16x. And when I divide by 16, we should get that x equals 5. Let's see, 5. Yep, x equals 5. All right, another definition, a line that is simultaneous means at the same time, so it's tangent at the same time to 2 or more circles. We call that a common tangent. So a tangent line that 2 circles have in common, it's tangent to both of them. We can have a common internal tangent or a common external tangent. Okay, so if the tangent line goes in between the 2 circles like this, so it touches this circle here, touches that circle there, that's called an internal tangent. An external tangent is if it's on the outside, like this. Goes outside both circles, not in between the 2 circles, that's called an external tangent. All right, so we've got a theorem here on the back page. It says, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So that's a lot of new stuff there. Let's draw that out. This is going to be really important. This theorem comes up a lot on the ACT. Okay, so we've got a line that's tangent to a circle, meaning it's touching at this one point right here. It says, if a line is tangent to a circle, then it's perpendicular to the radius. So if I draw in a radius, it's perpendicular to that radius drawn to that point where the tangent line hits the circle. The point of tangency is the point where the line hits the circle. So all it's saying is if I have a tangent line and I draw a radius to that tangent line, those two things are perpendicular. It says the converse is also true. So if you don't know if it's a tangent line, but you know that the radius is perpendicular to that line, then you would know it's a tangent line. All right, so it says determine whether or not AB is tangent. So we basically have to determine if this radius is perpendicular to this line right here. So to figure that out, we add up these two angles. And we know that, so we've got 89 degrees. We know that a triangle adds up to 180. If I subtract 180 minus 89, that does not equal 90 degrees. So this is not a right angle. So this is not tangent. All right, over here we're given the side lengths. So only when we're given degrees are we going to add it up and see if it equals 180. When we're given the side lengths, we're going to have to use Pythagorean theorem. So we want this to be a right angle right here. So I'll draw that with a question mark. That means our hypotenuse is 13, our legs are 12 and 5. So we need to see if 12 squared plus 5 squared equals 13 squared. 12 squared is 144, 5 squared is 25, 13 squared is 169, and 144 plus 25 does give us 169, so that does work out, which would mean that would be a right angle. So yes, this is tangent. All right, and letter C, this is our radius. It's 8. Notice that we're not given this piece right here, but since this is also a radius, that has to be 8. So we add those two together. That is our should be hypotenuse, because we're checking to see if this is a right angle or not. So that's our hypotenuse. This is a leg. This is a leg. So we need to see if 15 squared plus 8 squared equals 17 squared. 15 squared is 225. 8 squared is 64. 17 squared is 289. And these two added together does equal 289. So yes, this also works. This is a right triangle, which means this is a right angle, which means AB is a tangent line. This one over here doesn't look tangent, doesn't look like it's hitting at exactly one point. It looks like it's kind of going to go like this and maybe hit at another point over here, but we have to check to make sure. So this is 9, which means this radius is also 9. We want this to be a right angle. This plus this is 16, and our legs are 9 and 12. So 9 squared plus 12 squared, we need to check if that equals 16 squared. 9 squared is 81. 12 squared is 144. 16 squared is 256. 81 plus 144 gives me 225, which is not equal to 256. So this is not a right triangle, so it's not a tangent line. All right, and one last theorem for today. If two segments from the same external point, so we've got a point outside the circle, are tangent, so these two segments are meeting each other outside the circle, but they're meeting the circle at one point, which makes them tangent to the circle. So both of these segments are tangent to the circle, and they're meeting at a point outside the circle. That means those segments are congruent. And again, the converse is also true. So if you have two segments that are congruent, meeting outside the circle, then they are tangent to the circle. So if we've got this situation, this ice cream cone looking situation, that's how I remember it. Those two pieces are congruent. They're meeting outside the circle. They're both tangent to the circle. It tells us that the line segments are tangent. So all we do to solve is set those two things equal to each other. Get all the variables on the same side. Get all the numbers on the same side. So this cancels, 8 plus 2 is 10. 7v minus 3v is 4v. Divide by 4. We could either reduce that to 5 over 2 or turn it into a decimal, 2.5. All right, over here, both of these radii are both the same because they're both a radius of the circle, and we know that radii are congruent in the same circle. So since this is a radius, again, we can set this piece equal to the other radius. So we've got, when we subtract the x, we've got -1 equals 2x minus x is x minus 7, so we would add the 7. So x would equal 6. Okay, so now that we know x equals 6, 2 times 6 is 12, so we know this piece is 12. Since this piece is tangent to the circle and is meeting this piece right here, and this is also tangent to the circle, we know that these pieces are equal. So if 3y equals 12, then when we divide by 3, y equals 4. So then we need to find AB. It's asking us for this. Well, we know x is 6, so we know this piece right here is 6 minus 1, which is 5. And we know this piece is 2 times x, which is 6, so this piece is 12. And we know this is tangent, so this is a right angle. So we've got a right triangle. We're trying to find the hypotenuse, so we use the Pythagorean theorem. 5 squared plus 12 squared equals, we'll just call it AB squared. 25, 144. 25 plus 144 is 169. And then to solve for AB, we're going to have to take the square root. So we've got AB is square root of 169, which is 13.